Okay, today we're going to be doing some examples from the Working in Energy unit to help prepare for the free response summative. So this is a good video to watch if you wanted to see some examples done from beginning to end. So here's one example where we have a 5 kilogram block that's dropped onto a spring that has a spring constant of 980 newtons per meter. And we also know that we want to figure out how much the spring is compressed when the block comes to a rest if it's dropped from a height of 50 meters from where it ends up. Okay, so the first thing I like to do for these problems is I like to cross out anything that energy storage modes that I know we're not going to be using throughout the problem. For example, here we're told that the velocity is 0 both in the initial and final parts of the problem. So since that has to do with kinetically stored energy, we can go ahead and cross those out because we know that it's not really going to play a factor in our calculations. Similarly, we can also get rid of the friction here, and that's because, or E-thermal, because there's no opportunity for friction to act. Okay, now the next thing we want to do is identify our system, and you're answering the question throughout the course of the problem, what items, what objects store energy? One way to think about that is if you know you're going to have to use the gravitationally stored energy column, then that means that the object is part of your system as well as the Earth. And we also know that the spring stores energy at the end of the problem. So we're going to go ahead and go with the spring as part of our system because we for sure know that the spring energy is there at the end. Okay, so the next thing we want to do is create our LOL diagram, and we can tell that we are going to have energy stored initially gravitationally, so I'll just throw 4 blocks here. And we know that the spring is going to not yet be compressed, so there's no energy stored in the spring at the beginning of the problem. However, there is energy stored in the spring at the end of the problem. So I'm going to put some blocks here, not all of them yet, because we want to see if there's energy stored here. And we can tell that there will not be because this is a height of 0 where it ends up. So we can go ahead and cross this out, and that means since we can't identify any outside forces acting on the system, we can go ahead and feel free to put our last block in the ES column. So we have an LOL diagram that's going to help us figure out how to go about this problem. Because what we really need to know is, what is this X? How much is it compressed? So the final equation of this problem is likely going to have to do with this calculation here. But you'll see that if we start plugging things in, so here's my spring constant, is 980 newtons per meter. We won't have enough information yet because we don't know how much ES is. So we need to look elsewhere to figure out how much energy is in these 4 boxes of energy. Now, we see 4 blocks of energy on the left-hand side of the LOL diagram here in the gravitationally stored energy column. So let's just go ahead and find that and just see what happens. So we know the gravitationally stored energy is equal to the mass times 9.8 newtons per kilogram times whatever height it was. So here we have 5 kilograms, 9.8 newtons per kilogram times a height of 50 meters. Okay, so what I'm going to do now is I'm going to go grab my calculator, and we're going to do 5 times 9.8 times 50, and that gives me 2,450 joules of energy. So if I know that this is 2 1,450 joules of energy, this must also be the same amount. And that's the key part of this, and that's where we're using energy conservation. Whatever you have on the left is equal to the right as long as you have no working happening to the system. So what we're going to do is finish up our calculation here. I'm going to get x by itself. Okay, so first we'll take care of this half by multiplying the left by 2. And then divide to the other side by the 980. So we have to take, at the end of the, well, near the end of the day, when we move this stuff over, what happens is we just need to take the square root of 5 meters squared here. Okay? So when we take the square root of this, what ends up happening is we end up getting a value of 2.2 meters. And I'm just rounding to the tenths there. Okay, so that's one example of an LOL diagram problem. Okay, time for our second example. This example is going to have to do with using the thermally stored energy column. Okay, so we want to make an LOL diagram first, and let's first start off by getting rid of things that we know for sure is not going to be used. So right off the bat, there's no spring, so I'm going to go ahead and cross out the spring energy columns because it's just going to get in the way. When we look at the picture, we can tell what's going to be in play if you know your definitions of the energy storage modes. For example, in the beginning, we know there's gravitationally stored energy because it does start off with a height of 6 meters. And we also know that the kinetically stored energy has to be 0 because the velocity is 0 up top. Now, that allows us to say that we are storing energy in both the ball and the earth here, because we're going to go ahead and put all 4 blocks there. Now at the end, we have some hints to help us. So first up, we know that there's no gravitationally stored energy because this is a height of 0. We know that it's going to be moving because of the arrow there. That's exactly what we're finding. We want to figure out the velocity. And the problem straight up tells us that there's 44 joules of thermally stored energy. So we're for sure going to be using this column. So I'm at least going to throw in 1 block here. Okay? And then we'll throw the other 3 blocks into this column. That way we have our 4 blocks and 4 blocks. I'm going to go ahead and label the fact that we have 44 joules of energy here. And what you want to do now, just like in the last problem, figure out as many columns as you can. Because the thing is that we already know that our final step to this problem is to get that velocity. So like in the previous slide, we can go ahead and try to solve for that velocity, but we're going to get stuck here because we don't know what this EK is. We don't know what that EK is at this time. So we need to use the other columns and figure that out. One good place to start is any other column that you don't know the value to. So let's go ahead and find the EG in the beginning. That's going to be the mass of 5 times 9.8 newtons per kilogram. Oh, I'm sorry, that's 5 kilograms. And then we've also got a height of 6 meters. So when we do this calculation on our calc, what we end up getting is 294 joules of energy. Okay, so this is 294 joules. This is the most important part of the problem here where we're using conservation. Since we know there's no working being done, and that means that we're not adding to the system or taking away from the system in terms of energy, that's enough for us to make a pretty good shot at figuring out how much is in this column here that we are interested in. And it just so happens if we take the 294 and remove the 44, whatever is left over has to be in our EK column. So let's go ahead and do that. In my calc, I got 294 minus 44, and that gives us 250. So now it's not a mystery anymore what this column is worth. It's 250 joules. So we're going to go ahead, and now that we know what this is, we're going to, well, I'm just going to cross that out because now we know that this is 250 joules. And we can go ahead and solve for the velocity here. Okay, so I'm going to divide a half and the 5 kilograms from both sides. These go away, these go away. So at the near end of the day, we're going to do 250 divided by 2.5, and that gives us a nice 100 to take the square root of. So once we take the square root, we get a nice even 10 meters per second as our answer. Okay, and there you go. There's one example where we're using the thermally stored energy column to solve for an unknown. Okay, so you want to use the thermally stored energy column if I ever tell you that there's friction happening. All right, so I hope this was helpful, and I'll see you in class.